Actually, we have just one slide remaining for the chapter of coding. So on Tuesday, we mainly talked about the error detection and correction capability of channel coding. So basically, we looked at the coding from the theoretical perspective, but we did not go into the very details of the design of the coding or the information theory behind that. We just touched the bare surface about the theory that is used to guide the design of channel codes. Okay, so specifically, we first talk about the error detection capability and the error correction capability, and which is determined by the minimum Hamming distance of a certain code. So it doesn't matter whether it's linear block code or convolutional code or turbo code or some other code, we can always find out their minimum Euclidean Hamming distance. And once we know the minimum Hamming distance, then we know immediately about the error correction and detection capability, right? So the error detection capability is dm minus 1, and the error correction capability is dm minus 1 divided by 2, and then we take the floor. All right? So the basic idea here is quite obvious. The design of a channel code is just to maximize the minimum Hamming distance, okay? But that's not an easy task, obviously. So one of the commonly used theory for the design of channel code is the algebra, okay? And the foundation of algebra is the vector space. So because for all the sequences, they can be considered as, put them together, they form a space, right? You have a question?
Is it possible to demean is an even number?
The demean, it could be an even number. It could be an even number, it could be an odd number.
Then if we divided it by 2,
that's why we have the
floor operation.
We just take the integer part, okay? So demean could be even or odd. There are no restriction there. And so for all the length n sequences, we put them together, we have an n-dimensional vector space. And our channel code is just a subset of that space. And we would like our subset to be a subspace. In order for the subset to be a subspace, it must satisfy two conditions. The first condition is 0 must be an element of this subset, and the second, it must be closure in summation. So we have any two elements in the subset, we add them up together, and the result should still be in the same subset. Okay, so that's called a closure in summation. And if it satisfies these two properties, then it's a subspace. And for a linear block code, it's always a subspace, and we can actually verify that by using the generation matrix. Okay. So, and also by using this subspace, on Tuesday I proved that the minimum Hamming distance of a code equals to the minimum weight of all the code words, right? And that makes the calculation of the minimum Hamming distance a lot easier, right? So you just find the code word with the least number of ones, and then this code word tells you what is the worst case performance of this code, right? So NK linear block code, we talked about the geometric representation, and then we spend most of our time talking about two different optimal receivers. One is the optimum soft decoding. Okay, optimal soft decoding, we directly use our received information to perform decoding, and this optimal soft decoding is essentially to minimize the Euclidean distance between the received code word and one of the possible code words. Okay, so optimum soft decoding is to minimize the Euclidean distance. And also we have the optimum hard decoding. So for optimal hard decoding, once we receive the information, we first quantize them into ones and zeros, or one or negative ones. So we have a binary sequence. And since we have a binary sequence, so the optimum hard decoding, still by following exactly the same principle, the maximum likelihood decoding, we found out that it's equivalent to minimize the Hamming distance. Okay, so we either minimize the Euclidean distance or we minimize the Hamming distance. Depends on whether our information is soft or our information is hard. Okay, so the soft decoding is the optimal decoder. It will give us the best possible performance. Okay, and the Hamming, the hard decoding will have some performance loss. Okay, but in order to perform optimal decoding, it's not that easy, because it means that we need to search all the code words and find the one that has the minimum distance to the received information, right? And how many code words do we have? We have 2 to the power of k code words. If k is small, that's fine. However, if k is big, we can't do that anymore. Then we need to utilize the structure of the generation matrix or the parity check matrix to do suboptimal decoding. Okay? And one example of that is actually called message passing decoding, which is the decoder used for LDPC code. It's using the special structure of the parity check matrix. It's using the special structure of the parity check matrix to do an iterative decoding. Okay? And its performance is very close to the optimal decoding, but it's still not as good as the optimal decoding. But optimal decoding is essentially impossible for LDPC code with k on the order of a few thousands. Okay, can't do optimal decoding. So that.
I have a question.
Yes.
Dr. Wu, I have a question about homework.
Yes.
Started.
That's fine.
We got a homework and the project back, and for some reason we still don't have project number 2.
Okay.
Back.
I'm gonna go check.
Okay. Also, we don't have homework number 10, but however, we have homework 11 back, and homework 11 which we just turned in this Tuesday, and it was not graded.
Oh, okay. So I must send back the wrong pile then. So yeah, why don't you guys send them over to me again, and we're gonna grade them. I thought those are, I must mess up between homework 10 and 11 and give you back the wrong one.
Oh yeah. Okay.
Okay.
Okay. All right. Thank you.
All right. Okay. So let's continue. So we talked about the 2 decoding mechanisms, and the last topic that we talked about on Tuesday was the error probability, and we talked about 2 different types of error probability: message error probability and beta error probability. Okay? So the message error probability is essentially the probability that the number of errors is larger than the error correction capability. Okay, is larger than the error correction capability, and also we can get an approximation of the beta error probability. So that's an example here. So the final slide here is just a few examples of the specific linear block code. Okay, so these code are widely used in practice, and one category is called Hamming code. So for Hamming code, and it's n and k must satisfy this relationship, and it was obviously designed by Hamming himself. That's why it's called Hamming code. And n is 2m minus 1, and k is 2m minus 1 minus m. N and k must have this relationship, and it's not all of it. And once n and k follow this relationship, it also has a guideline about how to design the g and the h. So basically, given an m, we can have different nks, and we can design a code of different length. Okay, we can design a code of different length. And for Hamming code, it has been proved that the minimum Hamming distance is 3. Okay? So which means it can detect 2 bits of error and correct 1 bit of error. Okay, and as a simple example, if we put m equals to 3 here, if we put m equals to 3 here, that's going to be 7, and that's going to be 7 minus 3, 4. That's a 7-fold code, okay? And you can easily find this 7-fold code. That's the Hamming code in your textbook. And another commonly used code is cyclic redundancy check. Cyclic redundancy check, if you look at the name, it's called redundancy check. It does not do detection, it only do check. It does not do correction, it only do detection. It only do detection, okay? And it's usually used in the upper layers of a communication system. So we have the lower layer error correction coding and do its job, but still there is a chance that we are going to make an error even after error correction. Okay, and then we pass this information to a higher level, and on the higher level we'll do a cyclic redundancy check. Okay, and to see if there is still error. If there's still error, it will send back a negative acknowledgement and ask the transmitter to do a retransmission. So that's cyclic code. And again, there is a whole set of theories guiding the design of cyclic code. And another example is the Reed-Solomon code, as I mentioned last week, and it's usually in CD. Okay, it's usually in CD. And in addition, actually, it's also used in our cable TV, the digital TV system. Okay. Any question? So that's everything about channel coding, and we spend a lot of time here because channel coding is an important concept, and some of you have already taken the class of information theory, and information theory is the class about the design of channel coding, the design of source coding, and so basically channel has two theories, and the second theory is the channel coding theory. Okay, and talking about the design, actually it does not. It's talking about the performance limit of channel coding. Okay, and so for channel's theorem, the three theorems, what they tell us is the fundamental limit of a communication system. So those theorems tells us, given a communication system, how much information that we can transmit without error, okay, by using channel coding protection. Okay, for example, if the signal-to-noise ratio is 10 dB, channel theorem tells us what is the highest possible data rate that we can use to deliver information from source to destination without error by using channel coding, okay? And but the theory only shows us what is the limit. It does not tell us how to achieve that limit. And actually, he did achieve that limit, but he's using an ideal channel coding. And in his theory, in the proof of his theory, he's assuming that the block length of the channel code is infinity. Once it goes to infinity, and then he can prove that this is the best that we can do, right? And but in practice, we cannot use a channel code with length n being infinity. We have to have finite code length, right? So that's what the mathematicians, the communication engineers, we have all been trying during the past, how many years, 60, 70 years, trying to get closer and closer and closer to that limit. Okay, so those theories, they only tell us the fundamental limits, but didn't tell us how to do that. And it's up to us to figure out how to do that. But nowadays, we are getting closer and closer and closer to the limit. Okay, so now we are just a 2.3 dB away from the limit of channel. Okay. All right. Okay, so that's channel coding. And the final chapter of this class is the multiplexing and multiple access. And this is a relatively short chapter, and it's very easy compared to the previous chapters. So this is more like from a structure point of view of the communication system. Okay. So first we are going to have introduction, and then we are going to look at a few multiple access techniques, including FDMA, OFDMA, TDMA, CDMA, SDMA, and PDMA. Okay. So first of all, the reason that we need to have multiple access or multiple access is because we have limited resources. Okay, so the time and the frequency that is available for communication signaling associated within a given time is called the resource. Right? So essentially we have time and a frequency, and you can imagine that as a two-dimensional resource plane. Okay, that's how much resource we have, and that's how much resource that we can use. And so if you consider time as x-axis and frequency as the y-axis, so we have a plane, and we can actually divide them. So usually, especially in 5G communications, we usually cut them into grids. So if this is time, and this is frequency, okay, so we cut them. In frequency, we can cut them into different channels, right? And different channels in different frequency band. So and in time, we can cut them into slots. Okay, in time, we can cut them into slots. And each of these block here, we call it as a resource block. A resource block. Okay. And if you look at the resource allocation papers that are published, you will find thousands of papers on different IEEE journals and conferences, and which are focused on how to optimally to allocate these resource blocks to different users. So we have multiple users, and obviously we cannot allocate this resource to a single user. Or another easy way to do is just we have, for example, 5 frequencies. We assign these 5 frequencies to 5 different users, right? So a more advanced way to do that is to allocate the resource dynamically, okay, based on the needs of the users, okay, and that's called scheduling. So at each resource block, which users should transmit. And it's not just the need of the user itself, because this is a complex system. We have multiple users. And especially for wireless communications, when one user transmits, it's going to affect the signal-to-noise ratio of another user because of interference, okay? If they are using, for example, the same frequency at the same time. So we need to be extremely careful in the design of the optimal scheduling algorithms to make sure that we can minimize the interference and in the meantime meet the requirement of all the users and also maximize the throughput of the entire network. So there are several things that we need to juggle around, need to fulfill all those requirements. So it's a pretty difficult problem actually. Okay, so so that's communication resource, and each one is called a resource block. And for the users, they share communication resource means they share the same area on the plane. Okay, so then the multiple access problem or the scheduling problem is just to decide when and where each user should transmit, which resource block should be allocated to each user. Okay, so multiple access is multiple users share the same communication resources. Okay, and there are 2 types of multiple access, and the first one is the allocation of the communication resources among the users are fixed. Okay, we do not do the allocation dynamically. It's just a fixed allocation. And the second type is the allocation of the communication resources among the users are dynamically allocated based on the needs of the users. Okay, we use both of them. And for the first one, the fixed allocation, a simple example of that would be our radio and our TV stations. We just allocate a channel to the radio station, and that channel belongs to that radio station. No one else can use that. So that's a fixed allocation. And another way of fixed, actually, it can be considered as kind of dynamic. It's actually our telephone. If you make a telephone call, actually that channel is allocated to you throughout this phone call, the duration of the phone call. So even though once you make the connection to the other end of the telephone system, even if you are not talking, and that channel still belongs to you. Nobody else can use that. Okay, that's why for telephone systems we pay by minutes. Okay, pay for by minutes, because it doesn't matter whether you are talking or not, that channel is fixed, it's given to you. And in that case, we actually don't need to worry about dynamic resource allocation. You don't need to worry about interference because nobody else will compete with you. So that's actually also a fixed allocation. But that channel was not given to you if you are not making a phone call, obviously. So initially there is a dynamic allocation, but once you get that channel, it's fixed throughout the duration. That's why the telephone system, they have a guarantee of quality of service. So once you get connected, once you get through, and you will have that line. Okay, so that's also can be considered as a fixed resource allocation. So for dynamic resource allocation, that's like the internet, and there's no guarantee of quality of service, right? And you send out a packet, it will be routed in the internet, eventually it will get to the destination. But there is no dedicated channel for you, right? There is no dedicated channel for you. And you are sharing resources with lots of other users. And the same thing for our Wi-Fi system. So for our Wi-Fi system, you will use your cell phone or laptop to access the Wi-Fi, and the Wi-Fi access point or the Wi-Fi router, it has resources, and it will dynamically allocate a resource to the users depends on whether you have information to transmit or not. Okay, so in this case, there is no dedicated channel for any given user. And in this case, the allocation is more complicated because we need to consider the competitions and the conflicts among the different users. Okay, so the objective of multiple access is to design efficient resource sharing techniques such that the total throughput is maximized and no area on the time frequency plane is wasted. Okay, so we would like to utilize the resource as efficient as possible. And we don't have a whole lot of resource to begin with. Therefore, we need to improve the utilization of the resource. Okay, and one of the key things for the design of the 5G wireless communication systems is how to efficiently utilize the limited wireless spectrum. We don't have that much spectrum, and how do we increase the efficiency of the spectrum utilization? Okay. So there are three ways to improve the communication throughput. And the first way is to increase EIRP or reduce the system loss to improve EB naught at the receiver. Okay, just like what we did at our link analysis. So to increase power, that will sacrifice our energy efficiency. And also, actually, if the users, they share the same spectrum resource, to increase power will also increase interference to other users, which is not a good idea. You can increase power, somebody else, they can increase their power as well. And the end result is your signal to noise ratio is going to be about the same, right? You increase your power by 10 times, and the other user, they also increase their power by 10 times, and your interference in this case is going to kick in. So the system, so for the next generation systems, the noise actually is not that important anymore, and we call it interference limited system. So for interference limited system, the term is used to refer to the case that the effects of the interference is so strong such that it dominates the effects of the noise, such that we can ignore the effects of the noise, because interference here and noise is there. It's just a small part. So we don't need to consider noise anymore. And interference will determine our performance. So in that case, we can't just simply increase the power, because in the end, it's the same result that you're going to get for interference limited system, right? So that's one way of do that, but it's not a very good way. And a second way is to perform more channel bandwidth, right? So that's obvious. You give more bandwidth to a user, and then the data rate can be a lot higher. But the thing is, we have only limited spectrum resource, right? And at each band we have, so at a carrier frequency, the available bandwidth at a certain carrier frequency is about 10% of the carrier frequency. I mentioned about that earlier, right? So at 2 gigahertz, we have about 200 megahertz that can be used to carry information. So and we have limited spectrum. We cannot just give all the spectrum to one user, and then that will be unfair to all the other users. We cannot just provide more channel bandwidth, okay? So the third way is to make the allocation of the communication resources more efficient. And that's the key here, to multiple access, scheduling, okay? So how do we use the limited resource to serve as many users as possible, okay? So that's the basic idea of multiple access. And the basic multiple access types, and the first one is frequency division. And so for frequency division, we just allocate a certain frequency range to a certain user, right? Specified subband of frequency are allocated to different users. And time division, specified time slots are allocated to different users. Code division, and the users use mutually orthogonal code. And space division. Space division is when we use antenna arrays. We have an array of antenna, and by using an array of antenna, we can actually steer the beam of the antenna to different locations. And in that case, we can just use one antenna array to serve multiple users simultaneously. Okay, and this is called beamforming, and it was actually initially a radar technology. So for radar, so if you imagine you have a radar, if we have a radar, and then there is let's see, an aircraft, okay, or a missile is flying, and the radar, it's usually use an array of antennas. And the antennas, in order to get a stronger signal, they will focus the beam of the signals to the location of the aircraft. But the aircraft is moving, so we need to use phase array. So many of you might have heard the term phase array antennas. So we can actually control the phase. We can control the phase, and such that the beam can be steered into different directions. And when the aircraft is moving, the beam can follow this aircraft. Okay, so that's how the radar is tracking the aircrafts, okay, or the missiles. So by using phased array antennas, we can do that, and the same theory can be used for communication. We have multiple antennas, and we can steer the beam of the antennas to different locations. And if we have many antennas, we can create multiple beams simultaneously. Okay, and each beam will serve a single user, and in this case, there is minimum interference among the users, and that's a very commonly used, I wouldn't say very commonly, it's one of the enabling technologies for the 5G communication systems, okay? It's called multi-user MIMO. MIMO means multiple input, multiple output. We have multiple antennas, okay? So basically we have multiple antennas, we have multiple antennas, and then we can send one beam to one user, and another beam to another user, and another beam to another user. So this is called space division multiple access, okay? And it's gonna be used for our 5G system. This concept has already been proposed for 4G systems actually, but it's not widely used. But for 5G systems, it's gonna be one of the key technologies, space division. Polarization division, this is mainly for optical signals. For optical signals, we have the two different types of polarizations, and they are orthogonal to each other, and we can use orthogonal polarization to separate the signals, okay? And very often, we do not just use a single one of them, and actually we use a multiple combination of them. And for example, very often we use FDMA plus TDMA. That's exactly the resource block that I plotted at the very beginning. We have both time division and frequency division, right? And we have CDMA, TDMA, and that's actually how our 3G system is designed. We have CDMA among different users, and then we have time division among the users. Actually, we also have FDMA on top of that, okay? So, so for our, that's the CDMA, FTDMA, CDMA, FDMA. And we can have all different kinds of combinations about these multiple access techniques, okay? So up to now, most of the multiple access techniques are called orthogonal multiple access, okay? So for orthogonal multiple access means there is an orthogonality between the resources between two different users, okay? So various signals sharing the communication resource should not create unmanageable interference to each other, okay? Which means the signal on one CR channel should not significantly increase the probability of error in another channel, okay? So the possible solution for multiple access is to do orthogonal, okay? So for orthogonal means, so we assign, for example, one waveform to user 1 and another waveform to user 2, and if their inner product is orthogonal, this delta ij is 0 if I equals to, it does not equal to j, right? So then we are fine, okay? Then we are fine. So that's essentially for orthogonal multiple access, we need the signals on two different users to be orthogonal to each other, okay? They could be orthogonal in time, they could be orthogonal in frequency, or they could be orthogonal in the code domain, or they could be orthogonal in a combination of these different domains. And to satisfy this relationship, actually there are many different ways to satisfy this orthogonal relationship. So one example is, so for TDMA, what we do is, so if this is time, so for user 1, so this is S1T, right? And for user 2, this is S2T, right? So they do not overlap in time, and if you multiply them together, and whether you integrate or not doesn't matter, you are going to get a 0, right? So that's actually exactly TDMA. But this TDMA can actually be generalized. It can be generalized. Another way of doing this is, these two signals are also orthogonal. So orthogonal does not necessarily mean there is no overlapping, okay? And for these two signals, still they overlap with each other. And if you do S1t, S2t dt, as we have learned in an earlier chapter when we introduced the concept of orthogonal signals, they are still orthogonal, okay? So as long as they are orthogonal at the receiver, we can separate them, okay? Because what we observe is S1t plus S2t, right? And of course, add noise. So what we do at the receiver is, in order to get S1t, we simply do S1t times RT dt. And in that case, you are going to get S1t squared dt plus 0 plus S1t times noise. The noise is always there, but the signal from the second user is gone. And what's remaining is just the energy of the first user. And in that case, we can detect, right? So that's also orthogonality. So the basic idea of orthogonal multiple access is just to make sure that the signal at different users, the waveform at different users are orthogonal. Okay, so this is time domain also orthogonal. We can also do this in the frequency domain. Simply by replacing this t with f, we have the frequency domain orthogonal, right? So this is one channel and that's another channel. There is no overlapping. Obviously, they are orthogonal to each other. Right? So orthogonal frequency domain waveform used by the different users is XIF, XJF, DF, and they add up together, and you multiply them. So that's the conventional FDMA system. Okay. So for conventional FDMA, so that's frequency, and we have different frequencies, okay, for the different users. And actually for OFDMA, and we no longer use this kind of non-overlapping allocation. We use an overlapped waveform in the frequency domain. As long as they are orthogonal, then we are fine, okay? And for OFDMA, the channels, they do have overlapping, but they are orthogonal, okay? So let's look at the different techniques. So first of all, for frequency division multiple access, which is super easy, FDMA, so we allocate different frequency bands to different users, and ideally there is no overlapping between the frequency band, and to make it safer, usually we introduce a guard band. The guard band is just a buffer zone between the adjacent channels to reduce adjacent channel interference, okay? A, C, I, adjacent channel interference, okay? We usually add a guard band. So that's FDMA, a very simple concept. So now let's look at OFDMA, okay? So for OFDMA, we are using mutually orthogonal frequency domain signals for different users. As I said, as long as the signals from different users are orthogonal, then we are fine, okay? So we are using, for each user, we assign it with a particular frequency, but instead of using a square waveform, we are using something else, okay? So the signal from each user, they will actually spread the entire spectrum, okay? So which means there is a significant frequency domain overlapping among the signals from the different users. However, the signals from the different users, they are orthogonal, okay? As long as they are orthogonal, then we are fine. So the basis function that is used for OFDMA is this one. Okay, it's square root of 1 over square root of t times e to j2 pi fkt. Okay, so if you look at this signal here, its central frequency is fk. Okay, so for the kth user, we assign it with a frequency of phi k. Okay, and these signals for different f. And actually, if the f satisfies some certain conditions, then these signals, they are mutually orthogonal to each other. Okay. So let me introduce those. So we have phi kt equals to 1 over square root of t ej2 pi fkt. And they are orthogonal not for any arbitrary frequency. Okay? So the frequency, they have to satisfy some relationship. The relationship is actually fk equals to k divided by n. k divided by nt here, right? Nt. So that's the frequency requirement. And let's see if this, and the duration of the waveform is from 0 to t. The duration of the waveform is from 0 to t.
Doctor, I have a question. Is
Capital N number of users, yes. Any other question? So for the signal from one user, it's 1 over square root of t e j2 pi of kt. Okay? And the duration of t is from 0 to capital T, because that's the duration of one symbol. Okay? That's the duration of one symbol. And fk has to satisfy this relationship. If you think about this signal, if we do not have the time limit, the signal just have a single frequency fk. However, because of the time limit, if the signal is limited in time, then it's going to have unlimited support in frequency domain. So this signal is actually going to occupy the entire spectrum. And if you perform a Fourier transform of this signal, and actually it's a sinc function. Okay, it's a sinc function. Because this is essentially a rectangle. This is essentially a rectangle signal. The width of the rectangle signal is t, and then times a complex exponential. And the Fourier transform of a rectangle signal, as we have reviewed, is a sinc function. Okay, and then you will ask about this thing here. And based on the property of Fourier transform, if you still recall, if we do a frequency shift, if we shift the signal to a different frequency, and then we need to multiply it with ej2 pi fkt. Okay? Any question? So this is, if you look at its spectrum, that's how it looks, a sinc function. If you look at its spectrum, if we perform Fourier transform, that's how the spectrum will look like. This is right here, fk. Okay, so that's the waveform in the frequency domain. That's the Fourier transform of phi k t. Okay, that's the Fourier transform of phi k t. Any question? So it occupies the entire spectrum. It occupies the entire spectrum. So now let's verify that this signal is actually orthogonal to each other. Okay? So we do phi kt, phi jt dt. Okay? We use phi k, phi j. We will have 1 over t e j 2 pi f k t times e to negative j 2 pi f j. Let's not use j because I already used it for the imaginary symbol. Let's use phi l. F L T dt. And the integration is from 0 to t. So we will have 1 over t from 0 to capital T ej 2 pi fk minus fl t dt. So that's the integration of this exponential signal. And the integration of exponential is simple. It's 1 over j2 pi fk minus fl ej2 pi fk minus fl t from 0 to capital T. Okay? 1 over t j2 pi fk minus fl ej 2 pi fk minus fl capital T minus 1. Okay, when t is 0, it's 1. Any question? That's just a simple integration. And in order for this thing to be 0 when k does not equal to 0, means we need to be 1 when k does not equal to 0, right? We need this to be 1. So what is the condition for this thing to be 1? By Euler formula, this is cosine 2 pi fk fl t plus j sine 2 pi fk minus fl t equals to 1. So which means the imaginary part needs to be 0 and the real part needs to be 1. So for a cosine, in which condition we will have a 1? Cosine 0 is a 1. Cosine 2 pi, cosine 4 pi. And in the meantime, sine 0, sine 2 pi, sine 4 pi, they are 0, right? So as long as fk minus fl times t is an integer n, so if this is an integer n, then we will have 2n pi. Then this condition is satisfied, right? So which means the space between the two frequencies needs to be n over t. And that's why if we do fk equals to kt, did I put a 2 pi there? Nt here. Nt. Oh, okay. Yeah, I made a mistake here. That should be t. T is already the duration. Yeah, it's the duration of the symbol. I was thinking of the something period. K over t, right? So fk equals to k over t, fl equals to l over t, then fk minus fl equals to k minus l over t, which satisfies that condition, right? So based on this, our ej2 pi fk minus flt will be 1. So the signal are orthogonal. Okay, the signal are orthogonal. So we have showed that the signal are orthogonal. So that's when k does not equal to L. When k equals to L, which is simple, fkt, when k equals to L, fkt conjugate itself is simply going to be a 1 over t, which is 1. Okay? So the signals are actually orthonormal. They are orthogonal, and also they are normalized to unit energy. We just proved that. Okay? So for these signals, their Fourier transform is actually a sinc function, and which takes the entire spectrum, which means there will be significant frequency domain overlaps. But the signals, they are orthogonal to each other. Okay? The signals are orthogonal to each other. So what we do is, for example, the information from user k is sk. We multiply it with 5kt. Okay? And then we can, all the users, they can transmit simultaneously. All the users, they can transmit simultaneously. And that's our received signal. That's the basic idea of OFDMA. Okay? OFDMA. Orthogonal frequency division multiple access. OFDMA. Any question?
So the spacing between the frequencies depends on the duration of pulse.
Yes, exactly. Any question? So ideally, we would like the space between two users to be as small as possible. Then we can cram in more users. But there is no free lunch, right? You cannot make it even small, because in that case, you will need to make your time duration as long as possible. So you gain something in the frequency, you are sacrificing something in the time domain. So there's no free lunch. Okay. Any other question? And this is OFDMA if all these SK are from different users. If all these SK are from the same user, This is exactly OFDM, orthogonal frequency division multiple access, which is the key technology for our 4th generation cell phone system, the LTE system, which means all of your cell phones have OFDM in there. So what is OFDM? That's essentially this equation there. Okay, by using the orthogonal waveform. Okay.
It's like using a whole bunch of frequencies for a single user.
Use the whole, so we transmit one symbol at a different frequency. So we have a sequence of symbols to transmit, and we transmit them at the different frequencies. Okay? So that's the idea of OFDM, which is the key for our 4th generation cell phone system. And this is written in continuous time domain, right? We have a time t. And in reality, what we do is we have discrete time symbols. If you take the samples, discrete time samples, discretize this t, and this simply becomes a faster Fourier transform. Okay? And we can actually prove that, but that's irrelevant to this class. And actually, some of you have already taken my wireless communication class where we introduced that there. Okay? That's essentially actually a discrete time Fourier transform there. All right, so any question about OFDMA? Okay, so the minimum spacing between the carriers is 1 over t, okay? Just like what we have discussed, okay? So OFDMA with the minimum frequency spacing, so that's 1 over square root of t, e j2 pi kt times small t, okay? Where we can have n carriers, okay? And the index of the carriers are from 0 to n minus 1, okay? And the received signal is simply just the summation here, okay? And OFDM-A, where the A means multiple access, okay? So here this M is different from this M. So this is orthogonal frequency division multiple access. Multiple access means from different users. And this is orthogonal frequency division multiplexing. Multiplexing means different information from the same user. Okay? So if all this information are from the same user, then the scheme is called OFDM. Okay? And OFDM has been used in many, many different places. Okay? And one of the main advantages is it's robust against intersymbol interference, which is something that we discussed in the chapter of bandpass model or baseband detection, where we talk about equalization, right? With ISI, we need to do equalization, and we introduced zero forcing equalization. However, with OFDM, we don't need to do equalization anymore. Okay, we don't need to do equalization anymore. And the reason that why we don't need to do that, actually, I explained that in wireless communication, and it's irrelevant for this class here. Okay, so that's OFDMA. Next, let's move on to look at TDMA. Okay, TDMA. TDMA is, again, very simple. So we divide the time into frames. Okay, so time is segmented into short intervals, and usually we segment the time into frames, and then each frame is further segmented into slots. Okay, multiple slots are in a single frame, and you put all the frame together, you have the entire time domain. Okay, so that's the difference between frame and a slot. Okay, usually we allocate different slots to different users in a single frame. Okay, so let's see, we have a frame, just as a simple example. So the time is divided into frames. Let's see, we have each frame, we have 3 slots. So that's frame 1, that's frame 2, and each frame has 3 slots, and the duration of the slots should be the same. So usually, for example, we assign the first slot to user 1, the second slot to user 2, and the third slot to user 3. Okay, and then in the next frame, we use the same allocation. So user 1, it will transmit its information every 3 slots. Okay, so that's the difference between slot and a frame. Okay, slot is smaller. Time division multiple access, different users are assigned different time slots. and it can only be used in digital communication systems, because for analog signal we cannot segment them. But for digitals, it's just 1 and 0s, which can be easily segmented. Okay, and for FDMA, it can be used for both analog and digital. There's no problem there. But for TDMA, we can only use that for digital systems. Okay, so we have the 3 different time slots, and we might also have guard intervals here. Okay, we might also have guard intervals here. So the first type of TDMA is fixed assignment TDMA. So for fixed assignment, each user is assigned 1 or more fixed time slots, and efficient when the data from the users are heavy, and it's inefficient when the data from the users are bursty. Bursty means sporadic, means I don't usually have data to transmit. Once in a while I have something to transmit, but majority of the time I do not have anything to transmit. Okay, so for the fixed assignment TDMA, it's used for our voice communications for our cell phone systems. So for our cell phone systems, once you make a cell phone call and you are assigned a time slot in a frame, and that time slot belongs to you. Okay, nobody else can use that. Again, even if you are not talking, as long as you get through to the other side, then that time slot is yours. Okay, because in general, for phone conversation, for voice traffic, we are talking all the time, right? So the traffic is steady in this case. So that's why we assign a fixed slot for the voice traffic. Okay, we assign a fixed slot for the voice traffic, and that's why the cell phone company, they will tell you every month you have 500 minutes, you have 1,000 minutes, right? Because that's how much time that you can have that slot. And for data, for example, if you do texting, if you do chatting, okay, web browsing, checking email, those are sporadic traffic, okay? You are not checking email all the time. You just do that once in a while. And in that case, there is no need to do a fixed assignment. Okay, that's why our data is charged based on the amount of data that you are transmitted. You have data cap at 2 gigabytes per month, for example, right? So anyway, we have these 2 different schemes, and they have their advantages and disadvantages, and they are applicable to different application scenarios. Okay, so for the fixed assignment TDMA, so here we have the different users, and so we have a mechanism that can switch to the different users. So we are still using the same frequency, just different time, right? So at the first slot, we will connect to the first user at both transmitter and receiver, so the information can go through the channel. In the next time slot, it will switch to the second user and go through, and so on. Okay. So we have the frame, and then we have the different slots. Okay, and each slot belongs to a single user, and if we amplify the slot, usually we have some preambles for control information. For example, what is the source address, what is the destination address, our cyclic redundancy check, some control information, they are here. Okay, and then we have our extra data. We have our extra data to be transmitted. So that's the slot. For wireless communication, we also need to have some pilot symbols that are known to both transmitter and receiver. And by using those pilot symbols, we can do channel estimation. Okay, because for wireless channels, we need to actually estimate the status of the channel. For dynamic assignment TDMA, is also called packet switching. Okay, for fixed assignment TDMA, it's usually called circuit switching. It's like we have hardware circuit between the transmitter and receiver. Okay, for dynamic assignment, it's for each packet we allocate it to a different resource. Okay, a user is assigned to a time slot only when it has data to transmit, and an advantage is better utilization of the channel and efficient for bursty traffic. Okay, however, disadvantage is it needs extra control scheme. Okay, and this control is done on a packet basis. So for each packet, we need to decide where to send this packet. And for the fixed assignment, we only need to do the assignment on a session basis. For each session, we only need to do the control, the setup once. But for the packet switching, we need to do this for every single packet. So the overhead is obviously higher. Okay? We need media access control to determine which user should transmit. Okay? So here is an example. If we use the fixed transmission scheme, we assign the users A, B, C, D to the 4 different slots in a frame. However, if user C does not have anything to transmit, this slot will be left blank, right? And if user B does not have anything to transmit in the next time, it will be left blank. So we have wasted time slots. So these are the traffic from the different users, right? So A has A1, A2, B only has B1 and B3, C has C2 and C3, D has D1, D2, D3, okay? So we have some wasted time slots. And with the dynamic allocation, we can simply just transmit them whenever they are here, okay? So we can save some extra time slots to transmit more information, okay? So, so most practical systems, they use a combination of FDMA, TDMA, and also for the 3rd generation system, we use CDMA, okay? For the 4th generation, we don't use CDMA anymore, but we use OFDMA. OFDMA is just a special case of FDMA actually, okay? So we do channelization. This is just the picture that I draw at the beginning. And each of these is called a resource block. And we need to decide which resource block needs to be assigned to which user, okay? So that's channelization, the dividing the time and the frequency into blocks, okay? So now let's do a simple comparison between FDMA and TDMA, just some very simple math, okay? And see what is the advantage and disadvantage of FDMA and TDMA, okay? So we consider bit rate equivalence, okay? So with the same channel resource and the same number of channels, FDMA and TDMA, they can support the same data rate on each channel. Okay, we consider this equivalence. Otherwise, the comparison would be meaningless. Okay, so assume the size of a packet is B bits, and totally there are M channels. Okay, totally there are M channels. So we need to deliver this B bits over M channels. Okay, so for FDMA, the beta rate of one channel is B divided by T. Okay, is B divided by T. So in this case, if the beta rate of one channel is B divided by T, and then the total data rate of all the M channels will be MB divided by T. Okay, so that's the total data rate of an FDMA system. Okay, any question? And let's consider TDMA. So for TDMA, the time are divided into M slots. So instead of have M frequency channels, now we have M time domain slots, okay? And then still, the size of each packet is B bits, okay? So previously, for FDMA, we have M channels, so we can transmit this much information. Information over T seconds, okay? And now, so that's FDMA. So for TDMA, we are transmitting everything in this entire spectrum. It's just we divide them into time slots, okay? We are considering the same bandwidth and the same time duration to make the comparison fair, right? So the B times T are the same. So we divide the time into different slots. And so that's how many bits, right? That's how many bits are in one packet. So we are transmitting, for example, in this case, M equals to 4, we are transmitting 4 packets, right? And the same thing here, we need to squeeze all these 4, each packet, into each time slots. So the duration of each time slot in this case will be T over M, right? So the duration of the time slot will be T over M. So in this case, the data rate at each time slot is MB over T divided by M, okay? Which is MB over T. So that's the data rate. And all these 4 slots, they have the same data rate. So the overall data rate is the same. It's MB divided by T. So for FDMA, the data rate of each channel is B over T. We are transmitting BT bits in T seconds, and we have M channels. So that's the data rate of FDMA, and that's the data rate for TDMA. And obviously they are the same. Okay. So with the same bandwidth and the same time duration, actually it doesn't matter whether we use TDMA or FDMA in terms of data rate. They can give us exactly the same data rate. Okay. So this is the beta rate equivalence. That's the beta rate equivalence. Any question? All right. So now let's look at delay. Okay. Let's look at delay. So in terms of beta rate, the FDMA is better. FDMA and TDMA are the same, but in terms of delay, actually the TDMA is better than FDMA. On average, TDMA has a shorter delay. Okay, so what is the delay? The definition of the message delay is W plus tau, where W is the average waiting time prior to transmission. Okay, W is the average waiting time prior to transmission, and tau is the actual transmission time. Okay, the transmission time is determined by the data rate. Okay, so the amount of data divided by data rate gives us the time required to transmit. Okay, so transmission time for packet for B bits in FDMA, it's simply T. Okay, it takes this entire T second to transmit one packet. It's T. And for TDMA, the transmission time is T over M. The actual transmission time is only T over M. Okay? So TDMA, first of all, it has a shorter transmission time. Next, let's look at the waiting time. Okay? The waiting time is more interesting. Okay? So let's just, we can calculate more complicated waiting time by considering the random arrival of the packets, right? And but here, let's just look at a highly simplified scenario. Let's assume that a new packet arrives at the end of each frame. Okay, so once we have a new packet arrive at the end of each frame, and then in the next frame we just transmit this packet. Okay, so in this case for FDMA system there is no waiting time. When a packet comes in, it gets be transmitted immediately, and the transmission duration is T second, and then at the end of the T second a new packet comes in, and we transmit it. Okay, so there is no waiting time. So the only delay incurred by FDMA system is just the transmission time. And for TDMA time, there is actually a waiting time. So for different users, your waiting time will be different. So for FDMA, we have a new packet comes in for each user, right? And none of these packets needs to wait at any time. They will be delivered immediately. For TDMA, still we have capital M packets arriving at time 0. Okay, so for the packet of the first user is transmitted immediately. There's no delay. For the second user, it needs to wait for T divided by M. The third user, 2T divided by M, and so on. Okay, so the waiting time of the Mth user is M minus 1. Okay, is M minus 1 T divided M. Okay, and what we are interested in is not the waiting time of a single user, it's the average waiting time of all the users. So the average waiting time of all the users in this case is just the average. 1 over M. M is from 1 to capital M. Okay, so that's the waiting time for all the users. And in that case, we will have 1 over M, T over M, summation of M from 1 to capital M, minus 1. Okay? Or T over M squared, M from 0 to M minus 1, M prime. Okay? So that's the summation of integer numbers. And we have a simple equation for that. It's m times n minus 1. Okay. So that's the summation of integer numbers. So in this case, we put them back together, and we will have half t 1 minus 1 over m. Okay? So 1 of the m get cancelled. So 1 over 1 minus 1 over m. Okay? So that's the waiting time. So now we put it back together. For FDMA, the total delay will be simply t plus waiting time is 0. For TDMA, the delay is half t 1 minus 1 over m plus t over m. Okay? So it's going to be half t minus t over 2m plus t over m, which is half t plus t over half m. Right? Simple math here, which is half t 1 plus 1 over m. Okay? 1 over m. Because 1 over m is always less than 1, so this is always less than t. Right? If 1 over m equals to 1, then this is t. Okay? So in terms of delay, TDMA system is better. Any question? All right. So that's for the delay. So we have a simple comparison between FDMA and TDMA. As you can see here, we used a very simple argument. Okay? And we didn't consider the complex random arrival. Actually, even if we consider the random arrival, we can still prove that the TDMA system has a shorter delay. And actually the delay, the best case scenario, when m goes to infinity, the delay of TDMA system on average is just half t. So if you have many users, then on average, the delay is just a half t. Okay? So it's half of FDMA. So that's called asymptotic analysis. If we let one of the parameters go to infinity, that can simplify our analysis. All right. So that's FDMA versus TDMA, and that's the discussion of the delays. Okay, that's the delays, and so TDMA has shorter message delay compared to FDMA. Okay, and code division multiple access, we assign different users with different codes, and the data in this case are transmitted on the same time and the same frequency. Okay, at the same time on the same frequency. The only difference is they are using different code. You can just imagine we have two waveforms, and these two waveforms are orthogonal. That's just like what I showed at the very beginning of the example. This example here. So we can have these two users, they transmit at the same time, okay, from 0 to t, and they are transmitting at exactly the same frequency, but their waveform are orthogonal. So for code division multiple access, it's the same idea. Their codes are orthogonal to each other. Okay, and the receiver extracts the information of the one user by using the signature code of that particular user. Okay, and there are two different types of CDMA: direct sequence CDMA, which is the one that will be used in our third generation cell phone system, and also frequency hopping CDMA, which is mainly used for military applications. And for our initial Wi-Fi system 802.11a, FH CDMA is also part of the standard. Okay, and again, the details of CDMA are given in the class of wireless communications. Okay, and SDMA, space division multiple access, we use the space separation to share common communication resources. And one example is people at two different locations can access the resource of the same satellite as long as the satellite has two different separate beams. Okay, so these originally was used for satellite, but nowadays for, as I said, for the next generation cell phone systems, we are going to use this kind of SDMA. Okay, it's called multi-user MIMO. Okay, we are using an antenna array to serve multiple users simultaneously. That's one of the key technologies for 5G systems. Okay, and that's actually everything that I have. And another thing that I didn't put in the slide is another enabling technology for 5G system is actually called NOMA. Okay, NOMA stands for non-orthogonal multiple access. So in the multiple access that I introduced in this chapter, we always require their orthogonality such that they can minimize the interference, right? But for the 5G systems, as we said, we have very limited resource. We don't have unlimited time, we don't have unlimited spectrum. But we want to support as many users as possible. So what do? We put many users at the same spectrum on the same time and using the same code. We are using non-orthogonal multiple access. And then we use advanced signal processing techniques to separate one user from another. Okay, so that's NOMA. And it has received lots of attentions during the past few years. Okay, so any question? All right, so actually that's all the technical contents for this semester. And on Tuesday, I'm gonna show you guys a video, and which is actually a lecture made by Professor David Shi from Stanford University, and he just received the Shannon Award this year. And the Shannon Award is kind of like the highest award that you can get in the area of communication and information theory. And every year there is just a single awardee, and everybody received that award, they need to make a lecture. And that lecture is the Shannon lecture. So next Tuesday, I'm going to show you guys the Shannon lecture. It will give you some idea about the history of communications and what is the outlook of communications. Okay, and the title of the lecture is The Spirit of Information Theory. Okay, and it will give you a high-level overview of communications that will put you in perspective about what you have learned in this class. All right, and then we will have no class next Thursday.
Dr. Wu, I have a question.
Yes.
So we're about to turn our homework in again. So are we gonna get it back on next Tuesday, or are you planning to post it on the blackboard so we can see that?
I'm not sure if you can get that back next Tuesday, but hopefully you can get that back by the end of next week. And also, let me see regarding Blackboard. So the grades are, so you guys are interested in the grades, basically, of the test.
Yes.
Okay. So yeah, I can do that.
Everything.
I can put everything on Blackboard next week. Okay.
That's very appreciated. And a quick question. Quick question. Next Tuesday we're gonna watch that video. So are we gonna have a review for the final or no?
We are just gonna have a very brief review of the final. The video is about 15 minutes.
Thank you.
Okay.
Okay. All right.
All right.
What about our final exams?
The final exam is just going to cover everything after test number 1. I'm going to give you more information on Tuesday. Okay? The what? You can check on UE Connect. It's there, I think.
I'm trying, but they changed the website and I cannot find this.
Oh. Then I need to find it out too. So I usually just log on there and find the date. So I will find out. Okay.